Good morning. My name is Joo Jung from Seoul National University of Korea. Thank you for inviting me to this special session. Today, I would like to give a presentation on the topic of workload optimization of garment production line using simulation-based hybrid optimization method. The presentation will first introduce the background and purpose of the study and the power consumption monitoring system. That is the basis of the data, and then explain the application and results of the simulation-based hybrid optimization method for the garment production line. In the era of the fourth industrial revolution, element technologies are rapidly changing the industrial scene. A smart factory is regarded as the final state of the fourth industrial revolution in manufacturing, and is being promoted with the trend of custom manufacturing, autonomous, and networked manufacturing. Although the garment industry has a global market size similar to that of the automotive industry, it is interesting that almost all garment factories in the world operate in a similar state. This is not much different than 50 years ago. Garment factories are highly labor intensive, with many workers gathering and working in specific spaces. Also, there is a characteristic that the product changes frequently. The performance of the production line is influenced by the sequence of operators and the performance of individual operators. In addition, the performance of each operator depends on the task's level of difficulty and the operator's level of skill. However, there are two major difficulties in the garment production line. The first problem is that it is difficult to measure the exact production quantity and working time. This is due to manual work measurement, which lead to human error, or lack of samples, and requirement of additional resources. Even today, almost all garment factories are experiencing this problem. Although new technologies have been applied, this is a level that automates aggregation. And another important issue is the balance of a production line. This is mainly due to the placement of operators, where there is no quantitative criteria for work level. This makes it impossible to judge and predict the optimal line configuration. To overcome these problems, most garment factories are trying to adopt a smart factory, but most of them are small and medium-sized enterprises, which is difficult in terms of situation and cost. So in this study, to optimize the productivity of the garment production line, a power consumption monitoring system is developed. And using the data derived from the system, we develop a data-driven hybrid simulation optimization model using genetic algorithm and bottleneck removal method. Next, I would like to briefly introduce the power consumption monitoring system developed in this study. The power consumption monitoring system consists of a data gathering part and a data analysis part. To collect sewing data, a power monitoring device was developed and connected to each sewing machine. The collected data is transmitted to the cloud server through a wireless communication and stored. Data analysis recognizes reference sewing patterns from stored data and extract tasks from the data based on them. The pattern recognition algorithm was developed as a hybrid algorithm by combining a combination of approximation method and dynamic programming. To evaluate the developed system, the line to be monitored was selected from about 50 garment production line in an Indonesian garment factory. To get the data, power monitoring devices were installed on every sewing machine in the line, where 37 operators were performing 44 tasks. The main evaluation objective is the task count. This figure shows the result of task recognition for the entire target line. The average recognition rate was 92.1%, and the highest was 99.6%. These results show that the power monitoring system reliably measured the number of sewing work by analyzing power consumption data. And this figure shows the distribution of operators' work concentration over time. It can be seen that the work efficiency is lowest at about 7 a.m. and 6 p.m. And the highest productivity showed between 4 and 5 p.m. Through this system, we can reliably analyze the quantity and time of sewing operations. Next is modeling of a simulation-based hybrid optimization method. Among the various factors for line balancing, line configuration, unit task time, and level of difficulty are factors determined before the production stage. So in this study, the optimization method was selected to replace the operators, considering the applicability at the production stage and the flexibility for line balancing. A workload is a load that is added to each process in the production system, and balance of the workload is essential for maximum productivity. Bottleneck occurs when the workload is not balanced on the production line, and by removing the bottleneck, the production line can be balanced. And this figure shows the conceptual diagram of a simulation-based optimization process. The procedure first finds the optimum sequence of operators by linking simulation with genetic algorithm. After that, the maximum bottleneck is removed by reflecting the constraints based on the workload. By applying the sequence of the operators with the bottleneck adjusted, the simulation is performed again and the workload is analyzed. The process proceeds sequentially until it is no longer possible to remove the bottleneck under the constraints. The simulation was modeled using a commercial simulator called AnyLogic. The simulation target was the same as the line tested for the power consumption monitoring system. The simulation was performed reflecting the actual production period of 22 days, and the unit operation time data of each process extracted through the power monitoring system was applied. Similar to the actual production line, the simulation model was built by reflecting the material supply process and the stack between processes. Parameters and constraints were applied to simulation and optimization. The work level was applied to simulation, genetic algorithm, and bottleneck removal. This figure shows the work level weight factors of tasks and operators in the target line. Genetic algorithm parameter reflected the result of the parameter study, and constraints considered the criteria of field experts. As described above, genetic algorithm optimization was first performed, and then bottleneck removal was followed. The bottleneck removal was conducted by alternating the operator of the largest bottleneck point with the operator of the point with the operator of the point satisfying the constraints. After the bottleneck removal for the target line was performed 9 times, it was no longer possible to find the combination that satisfy the constraint. Next is the workload optimization result. The figure shows the changes in production according to the optimization result. As a result of genetic algorithm, production increased by 15.1%, and by bottleneck removal result, production finally increased by 67.4%. Although temporary workload transition occurred in the process of bottleneck removal, it was finally removed. And this figure shows how the production line workload changes as the bottleneck removal progresses. Figure A shows the result of the first bottleneck removal. The workload changes as the operator at point 9, determined to be bottleneck, is shifted to the operator at point 22. Similarly, figure B shows the change in workload according to the second bottleneck removal. And figure A shows the workload changes during the entire bottleneck removal processes. And figure B shows the trend of each workload profile. In figure B, it can be observed that the slope of the trend line increases. The closer the slope of the trend line is to 0, the more the workload of the production line is balanced. As a result of comparing the trend of changes in workload and output, the two trends were almost identical. The result shows that workload and productivity are closely related. So in this study, using discrete-event simulation and hybrid optimization method, the simulation optimization model for garment production line was developed. We confirmed that the productivity of the garment production line could be improved by 67.4% through the developed simulation optimization model. This attempt could also confirm the potential for digital transformation of garment production lines. And we hope that the result of this study will be useful in the labor-intensive garment industry. Thank you for your kind attention. Thank you.